Let's jump right into this. We are unpacking a seriously bold new framework today. It proposes solving quantum computing's biggest, most frustrating bottlenecks by using something quantum mechanics traditionally absolutely hates: memory and history. It's wild, so let's get into it.
Here's our roadmap. We'll start with the hardware problem, introduce dynamic quantum bits, look at merging de Broglie and Everett, explore the pre-Dolph framework, touch on second harmonic generation, and wrap up with the idea of a sustainable quantum cloud.
Part 1. The quantum hardware problem, or the weight versus the work. To understand why this new framework even needs to exist, we first have to look at the massive pain point of actually trying to use current quantum computers.
Check this out. This is a real hardware run on the IBM's FES system. Instead of getting a nice, clean, crisp answer, you get this kind of messy, noisy spread of outcomes. See that broad baseline of errors right across the bottom? Yeah, that is the deeply frustrating reality of hardware decoherence.
But honestly, here is the real kicker. That messy calculation, it actually executed in just 10 seconds. Just 10. But to get those 10 seconds of actual work, the user had to sit in a grueling 66-minute queue. I mean, that weight-to-work ratio is just a completely crippling bottleneck for researchers.
All right, part 2, introducing dynamic quantum bits, reframing memory as a resource. So what's truly interesting here is how the author's solution completely flips the script on how we handle quantum noise.
It builds this really stark contrast. Standard qubits are, by design, inherently memoryless. They literally fight to erase the past, right? They treat history as pure noise. But these new dbits? They use explicit memory states and history functionals. They treat history not as a liability, but actually as a computational capacitor. It's a real game changer. So what exactly is a qubit? Well, it's an engineered system that essentially wraps a super fragile quantum process in a stabilized, memory-aware classical substrate. Basically, by explicitly coupling the qubit to its own history, it remembers where it's been in order to stabilize where it's going. Moving to part 3, merging de Broglie and Everett, synthesizing two foundational theories. To give these dbits some rigorous theoretical grounding, the author proposes a mathematical synthesis of two notoriously opposed quantum interpretations. First up, we have de Broglie's phase waves. This gives us an observed reality where particles actually possess definite trajectories. They're guided smoothly through configuration space by these resonant global waves. Next, we bring in Everett's many worlds theory. Now, this completely removes the idea of wave collapse. Instead, it suggests reality branches out into these decoherence-protected relative states, and that happens based strictly on the records held by an observer. And the author's math elegantly bridges these two ideas together. The dbit acts as Everett's physical observer, literally recording the world branching into its memory, while simultaneously being guided along deterministic trajectories by de Broglie's phase waves. So it basically becomes a physical, stabilized anchor in a branching universe. How cool is that?
Okay, part 4, the pre-Dolph resilient framework, engineering survival. Here, the author takes all that high-level physics and formalizes it into this aggressive, highly error-resistant engine.
This engine operates in 4 distinct steps to create a seriously powerful non-Markovian feedback loop. First, it writes history. Second, it provides resonant guidance. Third, it stabilizes the legacy. And fourth, it enforces quantization. Ultimately, what it's doing is using past survival data to shield the current quantum state against catastrophic noise. And the payoff here is absolutely remarkable. The source claims this mathematically proven stabilization results in a staggering 99.6% accuracy on simulated 20-qubit circuits. 99.6%. Just by remembering the past, it achieves this incredible, almost bulletproof stability. Part 5. Second harmonic generation, pushing nonlinear photonics. Now, moving from the theoretical stuff into actual application, the author applies these memory-stabilized dbits to some deeply complex physical processes. By mapping photon dynamics directly into the dbit framework, they successfully modeled specific materials. Take a look at the data here. Notice how V-graphene achieves a very high entanglement score of 0.78? That right there proves the framework's sheer power when applied to nonlinear optics. They actually manage this using a specific differential equation called a primal logic ODE,
Basically, it treats the photon's temporary virtual states almost like a memory capacitor, one that stores and releases phase. It orchestrates this highly complex entanglement without losing coherence.
Finally, Part 6, a sustainable quantum cloud, flipping the industry model. Let's step back from the heavy physics for a second to see how this translates into a real-world, highly disruptive tech offering.
The author is confidently pitching a cloud substrate here that delivers deep quantum simulation but completely bypasses the immense energy draw of supercooled physical hardware. It's a really bold vision. Quantum capability without the cryo tax.
So, why does this matter? Why should a business leader or an environmental engineer actually care about this quantum wrapper alternative? What's the real-world impact for us?
Well, by simulating complex quantum runtimes on classical memory substrates, users get circuits that are effectively 10 times deeper, instantly. That means zero Q times, massive savings on R&D budgets, and a truly drastic reduction in the power grid energy that modern quantum data centers demand. It's a massive win-win.
Which leaves us with a pretty provocative thought to chew on. If engineered history and memory can stabilize the quantum world this perfectly, and do it cheaper and way greener, will the next era of computing actually rely on raw quantum hardware? Or will it rely on the ingenious classical substrates that simulate it? Think about that one. Catch you next time.